We can oxidize aromatic compounds. Any alkyl side chains can be oxidized to the carboxylic acid using a strong reagent such as KMnO4 that we have listed here, and also the sodium dichromate, as long as they have a CH next to the ring. So the hydrogen on the carbon next to the ring, if that is present, we can do an oxidation to the carboxylic acid. So we're going to find the benzylic hydrogen, or the one that's next to the ring. Here I have 2. And what this reaction does with KMnO4 is we find that carbon, we're going to do a cleavage here, and we're always going to get the benzoic acid there, as long as there's a benzylic hydrogen present. So here is another benzylic hydrogen. As long as I have that, I can do the cleavage. We're actually going to cleave 2 here. We keep 1 carbon, I get benzoic acid. On this last one here, there are no H's, so this will be no reaction. Oxidizing benzene rings, we can also reduce them. Most of them are inert to oxidation and also reduction under typical conditions. So if you want to reduce benzene to a cyclohexane, you can do that, but we're going to have to use very strong conditions. The first example here, if I have this alkene with the benzene ring and I use regular H2, all that is going to do is reduce the alkene. It's going to leave the benzene alone. If I try to do a reaction with hydrogen gas, platinum, a whole bunch of pressure, so I have 130 atmospheres at room temperature, then I will reduce my benzene to the alkane, or the cycloalkane. I can do the same reaction with a different catalyst, rhodium over carbon at 1 atm, so that's regular pressure, atmospheric pressure at 25 degrees, and that will give me the same thing and get my cyclohexane. Either we need to have a high pressure reaction or one with a stronger catalyst. So if I do a reduction here, hydrogen with this acyl benzene, that's going to reduce my carbonyl to the alcohol. And if I do this Br2 reaction here, this carbon and the OH are electron donating. So they are ortho para directors. We're going to get 2 products. I get the ortho plus the para. And then with the original compound, if I have a carbon that's multiply bonded to the oxygen here, this is an electron withdrawing group, so it is a meta director. So all these reactions come together, we can do different organic synthesis. We can create molecules by designing them. The synthesis can produce new molecules that we need for drugs or different materials. We can use them to improve efficiency and safety of known molecules. And highly advanced synthesis is used to test ideas and methods, and also can answer different challenges. So in order to propose a synthesis, you really need to be familiar with your reactions. So we need to know what the starting materials are, or what they begin with. We need to know what the products are. What reagents are used. And then any limitations. So limitations might include the Friedel-Crafts reactions, where we can't do them if an NH2 is present or an electron withdrawing group is present. So doing synthesis combines these different reactions that we have in multiple steps to give us a specific product. So when you plan a synthesis, one of the things you want to think about is, where's the next group going to go? In this case, the CH3 group is a methyl group, or R. That is an ortho para director. So that's going to direct at the green arrow. The nitro group is an electron withdrawing group. So it's a meta director, and that's going to direct to the same position. So in this case, when we're doing this, if we want to try to figure out what the next step is, we lucked out because both of the groups on the benzene ring are directing to the same position. So we'll get 1 Br added to give us 2 bromo, 4 nitrotoluene. And here, if we're looking at where does the next group go, in this case, our groups are opposing each other. The phenol group has electron lone pairs, so this is an electron donating group, and it directs ortho-para. The para is blocked here, so it's going to want to go ortho. But our CH3 group is also an electron donating group and an ortho-para director. That's going to direct to the ortho group because that para group is also blocked. So in this group, our directing effects are opposing each other, but the stronger activating group wins. So if you look back to slide number 23, you can see that the OH is one of the stronger activating groups and it's more reactive. So that's going to be our driver. So that's the bus driver. So the next group that gets added is ortho to the OH group. In this example here, the directing groups again oppose each other. The CH3 is an ortho-para director, so it's going to direct it here. There's also an ortho position on the CH3 side, but this one's kind of blocked by the chlorine. So we can get two products here where it's ortho to either of the groups. So this one is where it's ortho to the chlorine. Para to the methyl, or we can have it ortho to the methyl group and para to the other chloral group. We can sometimes work backwards in a reaction and try to figure out what is a possible immediate precursor of p-bromobenzoic acid if you were trying to synthesize this molecule. Let's say I wanted to add the bromine first. Is the next group going to go to the right spot? And can a carboxylic acid can be put on the ring directly? So these are some questions you want to ask. And then you just kind of continue the process until you have benzene as the starting material. So if I was working backward, you can use this retrosynthetic arrow. If I put the bromine on first, then this would have to be here. And then I could put on, go back to the benzene here. So let's try putting the Br on first. To do that, I need bromine FeBr3. Bromine is an ortho-para director. I can't just put a benzoic acid ring on. We don't have any reactions for that, but I can put a methyl group on and then do an oxidation. This is an ortho-para director, so I can put a methyl group on. Let's put an ethyl group on, sure, why not? And I'm just going to put on the para group because that's the one that I want. And then I do my oxidation. To get the product. Okay, so let's see now if I can do it in a different order. So let's put the ethyl group on first. This CH2CH3 group is also an ortho-para director, so I can put my next group on. And then I can just go into this reaction here, do the oxidation to get the correct product. Sometimes the reaction is a little bit more tricky, especially when you have extra groups that are added, and they may not always work. So if you like to work forwards first, we can attempt that. You want to think about a couple of things, like this CH3 group is an ortho-para director. This is a meta director. The group that is meta is going to be Br, and then CH3 is not meta to that. So I think that NO2 will probably get added last. We also want to think that our CH3 group cannot be added if an NO2 group is present. So we should probably do that one first. So if we start with benzene, we can start with the Br. That's an ortho-para director. I can add the CH3Cl with the AlCl3. So we're going to do a Friedel-Crafts reaction. That bromine is an ortho-para director, and it's going to add the CH3 para, which is what I want. So now we have our bromine, we have our methyl group, and the last thing we need to add now is our nitro group, HNO3 sulfuric acid. And even though the bromine is an ortho-para director, the methyl is an ortho-para director. The methyl group is a stronger activator, so that's going to be the one directing, so that will give us our NO2 at the ortho position. And if you go back and you want to see if changing the order affects things, you could put the CH3 on first and the Br on next, and that will get you to the synthesis just fine. But we would not be able to put the NO2 on first, because then you couldn't do any of the other reactions. So the NO2 needs to be put on last. For another problem here, what is wrong with this synthesis? So I have a nitrile on the benzene ring, and then I'm trying to do a Friedel-Crafts reaction followed by a nitration to give us this. And the thing that I see that's wrong here is this cannot be added with the nitrile group because that's electron withdrawing. If you wanted to do this synthesis, we want to start with the Friedel-Crafts. This is a meta director, which works out because both of our groups are meta. And then here you could add the nitro group next. And then the CN would go on last, but we don't have a way to do that right now, so we'll just chalk that up to target molecule. We mentioned that synthesis can be used for drugs, and one of these are to synthesize pain relievers. Analgesics are pain relievers, can also be anti-inflammatory agents, and some of these steroids can be used for inflammation as well. And NSAID is a non-steroidal anti-inflammatory drug. So salicylin comes from willow bark and gets converted into salicylic alcohol, which we can see the structure of there. This can get converted to salicylic acid in the stomach and is corrosive to the stomach walls. And so after people had been drinking this willow tree tea bark and were having the effects of the salicylic acid, but also the side effects of the stomach, the chemists went in and added this group onto here to make aspirin. And because they found that this was good for reducing fevers and had analgesic effects as well as anti-inflammatory properties. So the aspirin is less corrosive on our stomach, but it can cause stomach bleeding. So some of these other drugs that are now used are ibuprofen and also naproxen, which you can see the structures of here. They bear some resemblance to the aspirin with the carboxylic acids here and here.